This video, the third in chapter 9, is on what we call the root and ratio test for determining convergence. What happens if we have a series like this, n equals 1 to infinity of 2/3 to the power n? Well, we don't there's not a way to compare it to the kinds of series that we have been looking at. These p series don't make a good comparison. So we need an alternate way to do this, and we also could have infinite series of this type, n equals 1 to infinity 2 to the n over n factorial. And there again, the integral test or limit comparison tests aren't going to help us out. So we're going to define two new tests called the root test and the ratio test. We're going to use the root test to examine the convergence of this series, and we're going to use the ratio test to determine the convergence of this series. So let's define them formally on the next blackboard. So the root test simply says that if we look at the nth root of the terms and take the limit, and that is less than 1, the series converges. And if that limit as n goes to infinity of the nth root of the terms is greater than 1, then the series diverges. So less than 1 converges, greater than 1 diverges, and if it equals 1, the test does not give any information. So the series we had on the previous blackboard, 2/3 to the n equals 1 to infinity. It is easy to see that the limit as n goes to infinity of the nth root of 2/3 to the n is 2/3 less than 1. Therefore, the series converges. And that series actually is also called a geometric series. Geometric series are just a series with a series of terms raised to the same quantity raised to a power, and when that quantity raised to a power is less than 1, so we can actually generalize this. If we have n equals 1 to infinity of a ratio r raised to the n, that is going to diverge if r is greater than 1, and converge when r is less than 1, and that's part of the proof of the ratio test. Let's look at, or the root test, excuse me. Let's look now at the ratio test on the next blackboard, its formal definition. So the ratio test is kind of similar to the root in that less than 1 means converge, greater than 1 means diverge, equal to 1 means inconclusive, but what we're looking at here is the limit of the ratio of the later term in this series to the term just before it. So let's take a look at the other series that we've started with, and that had the factorial in it, n equals 1 to infinity of 2 to the n over n factorial. So if we look at this required limit for it, so what's it going to be? 2 to the n plus 1 over n plus 1 factorial. N plus 1 factorial means what? N plus 1 times n, etc. So it's actually n plus 1 times n factorial, right? 5 factorial is 5 times 4 times 3 times 2 times 1, but that's also the same as 5 times 4 factorial. And we're dividing that by what? 2 to the n divided by n factorial. So if we invert and multiply, we're going to see that there's a lot of cancellation. So we have n factorial, 2 to the n plus 1, n plus 1, n factorial, 2 to the n. Let's rewrite this 2 to the n plus 1 in the numerator as 2 times 2 to the n, and then we see that there is a lot of cancellation, right? The n factorials cancel, the 2 to the n's cancel, and if we continue on the next blackboard, we see that we get a limit comparison of limit 0. 0 is okay here. It wasn't okay in a limit comparison test, but here in this ratio test, we compare the n plus first term and the nth term. 0 is fine, and that is less than 1, so this series right here converges. So this is going to be a short video. We're not going to do any more examples using root or ratio tests. Most of the examples are very similar to these two. We will wind up using the root and ratio test again later when we talk about series that have variables in them, which are called power series, or sometimes a special case of alternating series, and these come up in the next two sections. So this concludes this video.